Today we're going to take a look at volumes. We've been looking at area, so we've been looking at two-dimensional figures. Now we're going to look at three-dimensional figures and find volumes. So the basic idea is the same for lots of different, people treat them as all kinds of different things. Books sometimes present them as if they're all different. They're all the same. The idea is that the volume of a solid of a known integrable cross-section area, A of x, from x equals a to x equals b, is the integral of the area from a to b. So what you're doing is you're finding the area of one little cross-section, multiplying that times dx, so it has some thickness, so that's a tiny little slice of volume, and then you're integrating that, which adds up all the little volumes to give you the volume of the whole thing. Now, what kinds of cross sections can you have? Well, these are some of the most common ones. Squares, where area is side squared; rectangle, area is base times height; triangle, equilateral triangle. You may have forgotten that formula. We did that in honors geometry, and part of the reason I do it in honors geometry is because it comes up in calculus. Sometimes you'll get a circular cross section, and we'll talk about that. You also will sometimes get a semicircle. With the semicircles, the region that is actually given to you is almost never, actually, I can't think of a single time that it's ever the radius. A better formula for this one is area is 1/8 pi times the diameter squared. You're almost always given something where you can find the diameter, not the radius. And then an annulus, which is simply a circle inside of another circle. And it's the region between those two. You're just taking the area of the big circle minus the area of the little circle to find the area between the two. All right, we're going to look at several of these. So let's jump into this one. The base of a solid, and this is frequently the way it starts. The base of the solid is the region R enclosed by the graphs of y equals 2 sine x and y equals x in the first quadrant. So basically, when you're looking at a graph of these two things, it's like, I don't know if you guys have ever looked at like when you look at maps where you're going someplace, you're doing an overhead view, right? And what you're seeing is what's on the ground. You're not seeing, like, if there's a building on the map, it doesn't have the building coming up at you, right? But it really is. What you're seeing is that. You're seeing the footprint of the buildings and the roads and all that kind of stuff, right? So that's the part that you're looking at. And then it says each cross-section cut perpendicular to the x-axis is a square. So there's a part that's coming up out of that at you that makes the cross-section a square. Now, I have colleagues who spend literally a week or more on helping students understand what these things look like. Total waste of time, in my opinion. I mean, it's fun and it's kind of interesting, but is it helpful? No. All you need to know, you don't need to know what the whole thing looks like. You don't need to be able to visualize this in 3 dimensions. Would it be nice to? Perhaps. All you need to know is, well, how do I set these up? So let's do that. So we've got y is equal to 2 sine of x and y is equal to x. So we've got y is equal to 2 times sine of x. So that's going to go up like that and come down like this, etc. And then we've got y is equal to x, which is going to look something like that. So this part from y is equal to 2 sine of x down to y is equal to x is the footprint of this thing, right? That's the part that's on the ground. Now, if you take a cross section perpendicular to the x-axis, so I'm slicing, then the whole cross section is a square. Now that's just the bottom of the cross section. So what do we actually have? Well, if we were to take that out and look at it, this is the bottom, and the whole cross section is a square. Okay, do you need to draw that? No, you don't have to draw it. So, but you do need to know that this is a side of the square, right? So the area is going to be side squared. Now, in terms of x, this distance is going to be the upper curve minus the lower curve. So s is going to be equal to 2 sine of x minus x quantity squared. Once we have the area of that, if we multiply that by dx, now this has, it's not just a square, it's like, a piece of foam or something that's cut out in the shape of a square. It's got some thickness to it, so it has volume. So the volume is going to be the integral, and we'll figure out the limits of integration in just a second, of 2 sine of x minus x quantity squared dx. So in terms of what I actually do, I almost never draw this, and I almost never write out this formula. I do usually write out this formula. What is the area of what I have of the cross section in terms of x, and then I just take the integral of that. Sometimes I don't even write this out. I just go straight to the integral, and that's fine. However much work you need to show to kind of help you think through the process is fine. So now we need to know, well, where is 2 sine of x equal to x? And that's very much something that you're not going to be able to solve without a calculator. So obviously they're going to intersect at x equals 0. I can see that just from the graph. But this point over here, not so obvious. So I'm going to go ahead and graph those. Wake up. So I have 2 sine x. I should change that to sine. I'll keep most of that. I'm going to clear this out, and I just want x. And you can see it's even skinnier than the way that I drew it, right? So I just need to find this point of intersection to find my upper limit of integration. So calculate me the intersection. Oh, I wonder what units those are. I'm going to guess that's 1. I'm going to guess, again, I'm amused by doing this. That wasn't particularly close. 1.895, yada, yada, yada. And from there, we just need to chuff that into the calculator to find the actual volume. So I'm going to quit out of here. Notice that I don't need to save that x because it keeps that x in its head until I do some other calculation for x. So I'm going to have the integral from 0 to that x value of, I need 2 sine x. I'm going to be super lazy and go, that was y1 minus y2 I need that to be, oops, I need the parentheses squared with respect to x. 0.4 4, 5, 6. Which kind of makes sense. It was a tiny little sliver for the base, and our cross sections are squares, so it's not like they're rectangles that are 17 times taller than the base. The height is going to be pretty short as well. Okay, so that's cross sections. Let me just point out that if it said instead of a square that the cross section was a semicircle, what part of the semicircle would this be? It's the diameter, which is why I gave you that other formula. Okay? All right. Moving on to volumes of revolution. So here we've got the region between the graph of f of x is 2 plus x cosine x, and the line y equals negative 1 is revolved about the line y equals negative 1 over the interval from negative 2 to 2 to generate a solid. Again, I have colleagues who spend a long time teaching students how to visualize what that's going to look like. And I actually used to spend time teaching students how to draw it so that you could draw it in 3 dimensions. It isn't worth it. It just really isn't. Now, if you're going into engineering, is that something that you should probably get to where you can, think about and do? Yeah. But is it important for the calculus part of it? Not really. So I don't really know what 2 plus x cosine x looks like. So I'm going to graph those. So go back to y equals. So I want 2 plus x cosine x. And then I want my second graph to be y is equal to negative 1. And I'm only going to go from negative 2 to 2, so I am going to change my window just to go from x is negative 2 to 2. Oh, that's why I was off. The scale wasn't by ones. I can be excused for making such a horrible guess. All right, that's good enough. So apparently that's 2 plus x cosine x, and that's y equals negative 1. So we're going to take this and we're going to rotate that piece around y equals negative 1. I don't always take the time to draw these, but I think it's helpful, especially at first, and it doesn't have to be great, right? I just need something. So I've got, it looked kind of like that. And then y equals negative 1 was down here. So I'm taking this piece and I'm going to revolve it around y equals negative 1. Now, here's why I think it's helpful to have a drawing on volumes of revolution. This is y equals negative 1. So I always think about this, just like I do with area, I think about a representative slice. So if I took this slice, so sort of like taking this pen, right, and I revolve it around, well, what it's sitting on, revolve it around my finger. What is that going to sweep out as it goes all the way around? So if you were looking at this way, what has this swept out as it goes all the way around that? A circle. Exactly. And what part of the circle is this? It's the radius of the circle. So I know that the area of a circle is pi times the radius squared. So the area in terms of x is going to be pi times the upper curve, 2 plus x cosine x, minus the lower curve, minus -1, all squared. I'll wait to simplify that until I chuff it into my equation. Volume then is going to be the integral from -2 to 2 of pi times, that'll be 3 plus x cosine x, quantity squared dx. And this would likely, almost always these are calculator problems, just because the numbers get pretty messy. You could square this, and I'm thinking, the x cosine x, well, we could do integration by parts there, right? That's not so bad. But you're also going to have an x squared cosine squared x. I don't really want to do that. Especially since I'm supposed to make the polynomial be my u and the trig be my dv, and now I'm trying to find what is it that has a derivative of cosine squared. Nope, not going to do it. So again, we'll just grab a calculator, chuff that in. I've got all the pieces already in. So if I do a math 9, we're doing the integral from -2 to 2. I need to have pi. You know what I'm going to do? Can I put it in front? That's not what I wanted. All right, I'm going to factor out the pi, was what I was saying. So from -2 to 2 of 3 plus x cosine x. Since I simplified that, it's easier actually not to go back to the originals. There are so many parentheses. Make sure your squared's in the right place. And it's 115.261. And you're like, wow, that was way bigger than our last one. Yeah, think about it. There's a couple of things. One is the distance across is much greater. And I went from -1 all the way up to, at its bottom right here, this distance is 3 for the radius, and then it only gets bigger. So you've got a pretty big figure going on here. Volumes of revolution tend to be quite a bit larger than volumes by slicing. Okay? All right. Let's do another interesting one. The region in the first quadrant enclosed by the graphs of y equals cosine x, y equals sine x, and x equals 0. That's odd. They give you 3 different curves. Is revolved around the line y equals 2 to form a solid. Find its volume. All right. So let's sketch a graph of this. I only need the first quadrant. So I've got y equals cosine x, which starts at 1 and then goes down and then blah, blah, blah. Y equals sine x, which starts here and goes up. And x equals 0, which is the y-axis. Okay, it's this little shark fin looking thing. And it's being revolved around the line y equals 2, which is up here. Now, for me, I usually draw the axis of revolution dotted if it's not one of the borders of my region that I'm revolving. So this is up here at y equals 2. So that's y equals cosine x. This is y equals sine x. And way up here is y equals 2. All right. The primary difference between this example and the previous one is on the previous example, what we were revolving things about was one of the borders of the region, right? When that happens, your cross sections are going to be circles. But here, this line that we're revolving things around is not one of the borders of the region. You're not going to have a circle. If I take a little representative slice here and revolve it around that point right up there, what is it that you're going to have? So your line's up here, your region's here, and I'm revolving this around like this. What am I getting? So look at it this way. All the region that I'm sweeping out as I go around this way. What am I getting?
Isn't that one where you minus the bigger circle minus the smaller?
Yes. It's an annulus. People call it a washer because it looks like a washer. It's got an outer radius and then it's got a hole in the middle of it. So my area is going to be pi times the big radius squared minus pi times the little radius squared. The area in terms of x is going to be equal to, all right, so the big radius is going to be from my center out to the far edge. So that's going to be from 2 to sine of x, and I want to subtract it in that order. It's going to be pi times 2 minus sine of x squared minus pi times the inside radius, where the hole is, where there isn't going to be anything, is going to be from 2 down to cosine of x. So 2 minus cosine of x squared. At some point, part of your brain will say, wouldn't it be easier just to say, well, I can factor out the pi and then do this minus this and then square the whole thing? No, because you can't do that. Just like in the Pythagorean theorem, sometimes people are like, couldn't you just add a and b together and then square it and then take the square root of that and that would be c? I'm like, no, that would never work. You got to square them, then add them together. Same thing here. You have to square these and then subtract, not subtract and then square. The order is important. So my volume is going to be, I'll go ahead and factor out the pi, times the integral. We're going to start at x is 0, and we're going to end where sine and cosine intersect one another, which is at yes. And I'm going to have my big radius squared minus my little radius squared. Now, those can be done by hand. When you square it, you're going to have a sine squared x and you're going to have a cosine squared x. And if only it was a sine squared plus cosine squared, then you could just dump it and replace it with 1. It's not. It's going to end up being a positive sine squared minus a positive cosine squared. If you ever have to do one of these by hand, and I'm not going to take the time to do this, but what you would do is this. Let me write it over here. You'd use what we call the power reducing identities. Sine squared of x is equal to 1/2 times the quantity 1 minus cosine of 2x. That's related to one of the identities that you learned in pre-cal. I can't remember which one it is. I don't remember if it was from a double angle identity or a half angle identity. I don't know most of the identities from pre-cal because a lot of them don't really help calculus along. And then if you have cosine squared, interestingly enough, it's 1/2 of 1 plus cosine of 2x. So you can use those power reducing identities to get rid of the squareds. It's still kind of a mess and it's kind of a pain. Generally speaking, these are going to be calculator active ones. And in the interest of time, we're going to move on to, no, we're not. Because we're not doing shells today. We're going to do shells next week. Okay? That's another way that you can do some volume problems, volumes of revolution. Okay?